All right, let's start part B, and we're going to mimic the same analysis that we had in part A, except that the function description is different. So are the derivatives. So we will try to find a different pattern for the derivatives of f. And eventually we're going to try to majorize the n plus first derivative. And in fact, if you just look at the Taylor's theorem, so we're doing our estimate on Rn, the absolute value of Rn. So we need to sort of like majorize this quantity, n plus first derivative, evaluated at z. So our analysis is going to revolve around that. Okay, so but going back to the original problem, we're trying to approximate ln to 25, okay, by Pn evaluated at 125, okay. And we want to know what n should be. What is the minimal n? How many terms should I retain in the partial sum, or in the Taylor polynomial, in other words, so that the error would not be greater than 10 to the minus 3. Okay. So for that reason, why don't we list the derivatives here all the way. Let's just look at the first three derivatives for ln x plus 1. So if you follow the derivatives formula card, ln x plus 1 has a derivative 1 over x plus 1. Let's write it in the exponent form. So use the power rule, generalized power rule. So the derivative is going to be minus x plus 1 minus 2. So it's going to be minus 1 over x plus 1 squared. So whenever I take the derivative, I use this exponent form, but I have to put it back in the fraction form, okay, reciprocal form. Okay, so 2x plus 1 negative 3, so 2x plus 1 cubed. Let's do one more, okay, fourth derivative. So that's minus 6x plus 1 to the negative 4, which is equal to minus 6x plus 1 to the fourth, okay? All right, so now I'm trying to catch a pattern here, okay? Well, each of these derivatives come with the bottom x plus 1 raised to some power. Let's see how is it related to n. So when you have the first derivative, it's x plus 1 to the power of 1. When it's the second derivative, it's x plus 1 squared in the bottom. So it's the same as the order of the derivative. So it's going to be n. Okay. So I should put an n here. So let's try to catch the pattern in the top. So you have 1, negative 1, 2, negative 6. Well, first of all, it's alternating, right? Its sign is alternating. So I'm going to put an minus 1 to the power of either n or m plus 1, but I have to check which one. If you can nail one of them by looking at its sign, and the others would follow that. So, for example, f double prime is negative 1, so it's negative. So when n equals 2, this should be negative. So why don't we go with n plus 1, right? Because it becomes negative 1 to the power of 3 for n equals 2. That's negative 1. Here we go. I have a negative 1 here. In the next term, let's say f triple prime n equals 3. So this exponent here is going to be 4. That's positive. So I'm going to get plus that expression. Okay. So now I have to estimate. I have to catch the pattern for the numbers like 1, 1, 2, 6. Okay. So these are like known numbers. In fact, this is in terms of factorials: 0 factorial, 1 factorial, 2 factorial, and 3 factorial. Okay. 3 factorial is 6, 2 factorial is 2, 1 factorial is 1, and 0 factorial by definition is 1. So in terms of n, what is it? So when n equals 2, second derivative, you have 1 factorial. Third derivative, you have 2 factorial. So it's n minus 1 factorial. Okay, n minus 1 factorial. Okay, so this is the pattern for f, the nth derivative of f. And we need to write the n plus first derivative evaluated at z. Okay, here we go. Minus 1 to the n plus 2, n factorial, x plus 1 to the power of n plus 1, but x is z. So let me just change that. Okay. So now we will try to estimate this quantity here. Okay. And here, z is going to be a number between 0 and x. So z, in other words, is going to be a number between 0 and x. And x in this case is 1.25, right? So I'm going to go back and write 1.25 here. Okay. So copying this down all the way here, 0, z, 1.25. I'm going to try to majorize this quantity. Okay, I'm going to have a good upper bound. I need a good upper bound for this term. Okay. Well, first of all, the alternation is going to be absorbed by the absolute value, because -1 to the power of n plus 2 for any n, it's going to be either -1 or +1. So since we take the absolute value, it's going to disappear. And we have n factorial and then z plus 1 to the n plus 1. So we want the bottom smaller to majorize this quantity. So how am I supposed to choose z so that the bottom is going to be smaller, so that the overall fraction is going to be larger? Well, that happens with the lower bound of z here. So if z is 0, let's say, then this quantity is going to be less than n factorial, because the bottom becomes 0 plus 1 to the power of n plus 1. So that's 1. Okay, so this is a very nice bound for the n plus first derivative evaluated at z. So now let's go back here. I need to again estimate this Rn here, right? And I have a good estimation for that, so why don't we continue with it? So let me just write down Rn evaluated at 1.25. All right, so I just copied that down here for x equals 1.25. And remember that I have just a very nice estimate for this part. So that's less than or equal to n factorial. So we can go ahead and then say like this is less than or equal to n factorial, n plus 1 factorial. By the way, since all of these terms now are positive, I don't need to carry forward the absolute value sign. Okay. So this one can be written as 1 over n plus 1, 1.25 to the n. Okay. So now you can have a trial error. So for n equals 1, n equals 2, n equals 3, n equals 4, you can just write this quantity. To check if it's going to be less than 10 to the minus 3. So what is the n value for that? That's what we're after, right? For n equals 1, it's going to be 1.25 divided by 2. For n equals 2, it's going to be 1.25 squared divided by 3, 1.25 cubed divided by 4, 1.25 to the 4th divided by 5. Okay? So go ahead and then calculate those. All right, so I put those numbers in by using the calculator. I even looked at n equals 5 and n equals 6 cases. So at first glance, it looked like the error was decreasing in some sense, but starting from n equals 5, this error is increasing. That's bad because you're diverging away. So there's no way to make this quantity less than 10 to the negative 3, because this quantity here is going to grow substantially when you go to larger n's. So what does that mean in terms of the analysis here? That means that you cannot guess or you cannot estimate ln of 2.25 by using the Taylor expansion whenever x equals 1.25. Okay, that's sort of like the analysis and the result coming out of this. So which essentially means that ln 2.25 cannot be approximated by Pn at 1.25. No matter what n is, no matter how big n is. Because in the Taylor expansion, we want to keep as little terms as possible. But here in this case, even though you have like a larger n, that means you have like so many terms in the sum retained, there's no way to estimate the value of ln 2.25 with the error less than 10 to the minus 3. So in this case, the MacLaurin polynomial doesn't provide us anything good, okay? Not like in part A, okay? As an alternate, I can give you just one question for you to work on, and for which it will definitely work. This analysis will definitely work. Instead of estimating ln 2.25, why don't you estimate this? You can take this as a side problem. After you watch this video, you can start going through that. Why don't you estimate ln of 0.25, and that is ln of 125, okay? So here, in fact, part of the reason that the analysis didn't work earlier is that because we have the MacLaurin expansion at c equals 0, and what we're trying to make an estimate for is at 1.25 in the original problem. We are too far from the expansion, far from the point where we had the expansion, right? This distance is too far. But if you somehow get a good estimate around 0.25, so 0.25 is relatively closer to c equals 0. So out of this analysis, you will get a better estimate, and you'll be able to find a degree for which this approximation is going to work with less than 10 to the minus 3. But that's a side example. And after you watch this video, I hope you go through this example by yourself. All right. So this was a long video. I'm sorry, but we just finished it. That's the end. I'll see you in another video. Bye.